Are doing well. So let us continue our discussion on the double and triple integrals. In this lecture we are going to discuss further the idea of triple integrals and introduce a new notion which is called the surface area. Okay, so just recall in the previous lecture we saw that how to compute double integrals and triple integrals over regions which were rectangle for double integral and then box type region for triple integral, correct? And then we also saw that the region can be taken more general, okay, which is written over here, and we had this theorem which allows us to compute double integrals over regions of this type, correct? So one variable is basically moving between two curves given by a continuous function, and the other variable is moving over an interval, correct? So this was more general region than the rectangle which we discussed in the previous lecture. And similarly, there is nothing wholly about that only y can vary between these two functions. You can have x varying between these two functions, and then y will vary over an interval. Okay, so this was the situation, and then we saw that this can be used to compute some nice double integrals over some nice regions. So a similar idea also exists for triple integrals. Okay, so if you recall, in the previous lecture we had triple integrals only over box type regions. Okay, but there is a similar theorem which I am just going to state over here. Okay, so basically what the idea is, we want to incorporate more and more bounded regions over which we can compute the integrals. Okay, so what we do, as earlier, we take, let's say we take a bounded region in R3 because we are talking about the triple integral, and we have a nice continuous function so that we can talk about the integral. Now this region is bounded, so we can put it inside a box, isn't it? Because you can find a box big enough which allows you to have this E inside that box. Okay, so as we did in the previous situation, what we do, we extend the given function f from E to B. Okay, what we do, we just set it to be 0 on the complement of E inside the box. Okay, so we get a new function which we call the extension of f. Okay, so we define the triple integral of f over this bounded domain or region via this. Okay, so this capital F is a new function, and the box is the one which contains E. Okay, of course, when I say this, all these things should make sense. This integral has to make sense. This integral has to exist. Okay, but the advantage here is that capital F is a function and the domain is a box. Okay, and the definition we know. So once I have this, then I can talk about the triple integral over any bounded region. Okay, but this is not an easy situation. The regions in R3 can be anything, so we may not be able to always find triple integrals over a general enough given region. So what we do basically a similar thing, that we try to find some simpler domains over which we can compute the triple integrals. Okay, like we did in the case of double integral. So we are going to have a similar situation over here. So we say that if you have a region which lies in this fashion, okay, so if E lies between the graphs of two continuous functions of two variables. Okay, so in the previous case, what was that the domain or the region in R2 was lying between two graphs of continuous functions, but here we can have two surfaces because we are now in R3. So if our region is lying between two surfaces, because any function of two variables is going to give rise to a surface, isn't it? So it's going to look like this, that one component, let us say Z, is lying between two surfaces, and then xy is varying over a domain in the xy plane. Okay, so such regions we can handle, and we can compute the triple integral over such regions. Okay, so as I said, this D is nothing but this is the projection of E in the xy plane, and this u1 and u2 you assume that they are continuous functions, so that the surfaces which you get, they are nice. Otherwise, you know, we won't be able to compute the integral. Okay, so for such regions we can define, or I mean I should say that the Fubini theorem, okay, this can be written as a theorem. The Fubini theorem says that the integral of f, or the triple integral of f over such a region, is given by this. Okay, so what you do, you integrate out z between these two surfaces. Okay, whatever it is, this is going to give you a quantity in x and y. Similarly, this is a quantity in x and y, and this is a function of x, y and z. So I just integrate it out with respect to z. So x and y, they are constants. Okay, so this is like a single integral, and then the resulting thing is going to be a new function of x and y. Okay, so what you are going to get, you are going to get a new function for which you have to compute the double integral. Okay, so again you have to worry about that when I say that this is the projection, you know, the projection has to be nice enough so that you can compute the double integral. It should be one of the types, like it should be a rectangle, or it should be bounded between two graphs of a single variable function, isn't it? Because those are the things which we can you know, address, or we can compute. So that you always have to keep in mind, even though I'm not writing again and again those things, but whenever I write a double integral, I mean that the domain is such which has been you know, given to you in the form of Fubini theorem and so on. Okay, all right. And as I said, there's nothing holy about that, you know, you can just do it z. So it's like, you know, the top and the bottom is given by surfaces. It can be like sides also. So instead of z here, I can also have y, I can have x, and then the remaining two variables will be over here. Okay, so that you have to write. So when you had the Fubini theorem over a box, you know, those situations were there also. So you have to just write the other possibilities also. The domain E, or the region E, can be bounded between two surfaces along other planes also. Okay, it doesn't have to be the variable z. All right. Okay, so this is what I have written. The same idea will work when the roles of these variables are interchanged. Okay, all right. So we will look into some examples, but let me, before going to the examples, let me talk about the area, this idea of surface area. Okay, this is again a topic which, you know, double integral will come in. So what is the meaning of surface area? So just recall what we had situations that we are given a function of two variables, so it gives you a surface in R3, and then the idea of double integral was that it was giving us the volume of this solid, because so in the xy plane it is bounded by a domain. Let's just say this is a rectangle, and over which I have the surface. Okay, so this surface is given by the z equals to f of x comma y. Okay, so the idea of double integral was to compute the volume of this solid, isn't it? Now you know, so this is like you imagine, you know, a tent. Okay, and you know, put the curtains along the I mean, you just lower the curtains, so it gives you like a room. So you want to see that what is the volume of that shape. So but you know, there can be another question that we want to find the area of the top. Okay, now this is no longer a flat surface. Okay, the roof is not flat, so it's not going to look like a rectangle. Okay, or imagine a mountain top, or you know, something, a hill like Isar hill. So you want to measure the surface area of that hill. Okay, so it's since it's not flat, so we can't just do like you know, length into width. So we have to you know, do some more work, and that is what the idea of this surface area is. Okay, so we are interested in finding the area of any given surface. Okay, when I say any, we will see that only some nice surfaces we can handle in this course, you know, because then you need more machinery, more tools to you know, go about it. So what we do, we take up this question that how does one find the area of the surface. Okay, so now I am only interested in the area, because this is a two-dimensional thing. If I just look at the top, and we need to find the area. So idea, you know, will be always the same, that we know how to find the areas of squares and rectangles. Okay, so we have to somehow use that, and we have to, you know, use that to approximate this area, and then in the limiting process we should get the area of the surface. Okay, so since this is going to involve an approximation, so that is why we always assume that things are continuous and so on, so that finally when we write down the limit of those approximations, it makes sense. All right. So the in approximating or in finding the areas, volumes, or these integrals, the underlying area is always idea is the same, that you try to approximate it using the known ideas, isn't it? So this is what we are going to do. Okay, so we consider a function of two variables, okay, defined over a bounded domain, because we are interested in finding the area, and we assume that the partial derivatives exist. These partial derivatives, this condition is important, because otherwise we won't be able to make sense of many things, and finding the area will be difficult. Okay, so this is some assumption which we need. So the area of the surface, which is given by this equation, is given by this formula. Okay, so you see, this is a double integral over the domain of f, but we are no longer integrating f of x comma y. Okay, rather what we are doing, we are having this new function here. This involves the partial derivatives and their squares, and then plus 1 here, and then the square root. Okay, so you see that fx and fy are assumed to be continuous, so that this whole quantity we can talk about integral of this thing. Okay, so but you must ask this question, that how does one get this? Okay, so what I will do is, I will give you a brief sketch that how does one get such a form for computing the double area. Why not just the function? We know that if we just integrate out the function, we are going to get the volume, but we are just looking, we are interested only in the surface area. Okay, so this new thing comes up here, which gives you the surface area. Okay, so as I said, we follow the first principle. We write down the approximation of that surfaces via rectangles, okay, or some sort of thing which we can compute. All right, so let us look at the idea behind this formula. Generally the proofs are not involved in this course, but to appreciate such things, I think we need to see the underlying idea at least. Okay, so let us try to discuss in brief that how does one get this. Okay, so call it equation 1. All right, so in this definition, I have not, or in this formula, I have not said anything about f can be any continuous function, but for our convenience we are just going to take a non-negative function, because non-negative function, so that means you get a surface in the upper half plane. Okay, upper half space, I should say. So we take a non-negative function defined over, let's say, a rectangle, because we are just trying to sketch the idea, so we take a simple situation, and then this is the assumption which we had. Okay, so as I told you, that the idea of surface area, how does one compute the surface area, is more or less the same as we did in case of any other integral. Okay, it's the idea of approximation. So we try to approximate this surface locally by tangent planes. Okay, so this is something which you have to go back to the definition of tangent planes. So we have a surface, and then we can take a point on it, and then we can draw the tangent plane. Okay, so these rectangles or something which we can approximate are going to come from tangent planes, isn't it? So we know, when we were discussing the idea of tangent plane, we know that the surface is actually given, can be approximated via this by this tangent plane, which is this over here locally. So at any point a comma, you take any point a comma b, and then in a small neighborhood of that point, if you take x and y, then I have this approximation of f. Okay, via this linear equation. So this is very important. Okay, why? Because when I say linear equation, so I am going to get x and y. Okay, so x and y, so these are the length and width. So I am going to get the approximation of the surface at a point by a plane. Okay, but this is happening locally, so we have to basically choose several points, and then at each point we approximate the surface When we approximate the surface by length and width, that means we can approximate by these things called parallelograms, and we will get approximation of areas locally, and then we just sum them up. Okay, so this is the whole idea. So as always, what we do, we decompose or divide the domain which we were writing as D into smaller rectangles. Okay, so let us call these rectangles R, I say. So there are finitely many. Okay, I am not writing NNM, and we do it in such a way that the area of each one is fixed. Okay, so like delta x, delta y, this is the x variable and this is the y variable. So you take these smaller area of smaller rectangles to be delta A, which is delta x times delta y. All right, now look at any point over here. So in this picture it is a corner point, and then look at the corresponding image of this point. This is going to be a point on the surface. Okay, so this is what I have written over here, that we take any point. Okay, so for convenience we can take this point to be the center or a corner. Okay, this is up to you, but you fix some idea, like you want to take a corner point or the center, and then continue with that for other rectangles also, so that it becomes easy to write down things. Okay, and then look at its image. Okay, under the functions or the point on the graph of f. Okay, so this is going to be a point over here. Okay, now at this point what we are going to do is we are going to look at these tangent lines. Correct, so there are going to be two tangent lines, and that is what we are going to look at, and these two tangent lines are basically going to give us a parallelogram locally. Okay, so we know that this is part of the tangent plane, and this approximates the surface locally at the point this x, I and y, j. So if I compute the area of this parallelogram, then it gives me approximately the area of the surface around this point. Okay, and this is what we basically do. Okay, so we precisely use this idea and approximate the surface near the point which I just told you, and then we are going to get the area. So area of this parallelogram I am calling as delta Tij. T is basically the part of the tangent plane above this rectangle. Okay, so then what we get that if I sum all these areas of the part of the tangent planes, I should get the surface area. Correct, I should get an approximation to the surface area. So when I make n and m go to infinity, I should get the surface area. This is the whole idea which I was just telling you about. Correct. So what we do, we are going to get this point, and then you take another point, and then take a corresponding parallelogram. So you patch it up, and then at each point you are going to get this small parallelograms, and if I put them together, they should give me the surface area. Okay, but again this is a formula which does not have anything to do with the formula which we have a priori, isn't it? So we do that we try to see that what is this, how to find the area of this parallelogram, and then we can relate, because now you see that this quantity over here is nothing but the same if you recall the definition of a double integral. Okay, so this is like a double Riemann sum. All we need to see is what is this area here. Okay, that will give us that of which function. Okay, all right. So area of the parallelogram can be found, we know from our discussion on the cross product, that if I get hold of those two sides, the vectors, the area of the parallelogram is nothing but the magnitude of the cross product. Okay, so this is where again you need to go back to the discussion of tangent planes. Okay, so let A and B denote the vectors that start at the point and lie along the sides of the parallelogram, which is and of course the area is delta T, I say. So what are these vectors? Once we know these vectors, then we are done. Okay, so at this point we need to go back and see that these partial derivatives at these points, what do they give us? Okay, so these guys are precisely the slopes of the tangent lines, correct, which start at the point and you can go back to the picture. So these are the tangent lines, and the slope is determined by the partial derivatives, isn't it? So the slope is determined by the partial derivatives. So we can, using this idea, we can get that the vector A has to be this. Okay, this be set y equal to 0, correct? And this delta x, because again I think you should go back to the equation of the, because of this x, because that decides the length. Okay, so this is the slope and then this is the x component, so that is why this delta x is coming over here. So this is what the vector A is going to look like. So this is one side of the parallelogram and the other side is this. Okay, so we need to compute the area. So what you do, you compute the cross product of these two guys and take the modulus or the magnitude. When you do that, I get this, and then I get this delta x times delta y, which is the area component, isn't it? So if you substitute this quantity back into this formula and compare it with the definition of double integral, then precisely you get that basically this limit or this double Riemann sum is basically being computed for this function, and then delta x delta y. Okay, so that is the area component. So basically what we are going to get from this double limits, that area of the surface is precisely this double integral, because this is the function which we just got. Okay, so this is how you are going to get a formula for the surface area. Okay, so this I think is good enough justification for the formula. So you don't think that this just comes out of the blue and then you have to memorize it. No, one can sketch, one can give the reasoning. Okay, so the whole thing is, things no longer are like just delta x delta y. The contribution of f is going to be here, but this is going to be in terms of the partial derivatives over here. Okay, so this is a very nice idea and just approximation of the surface by tangent planes. Okay, that is the whole point. Okay, so let us look at some examples. So consider this. Okay, there is a picture here. You see, I am taking these examples from the book so that I can show you the pictures. Otherwise, if I draw with hand, it's not going to look this nice. Okay, so this is always important that whichever example you try to work out, you try to first visualize the picture, how the surface is going to look like and so on. So look at this surface. So z equals to x square plus 2y. So you see z and x, this is a parabola, and z and y, this is, so these cross sections are going to be lines, correct? So this is how it's going to look like, and then we are interested in this surface only over the domain, which is a triangle here in the xy plane with these vertices. Okay, so the triangle is drawn over here. So look at this domain and the part of the surface above this. Okay, and the question is asking you to find the surface area of this. Okay, over this region. So there are two things you need to worry about. The first of all, the partial derivatives should be continuous, which is very easy here to see, and the domain should be such over which we can compute the double integral, isn't it? So this is precisely the situation here, that this x varies between these two lines, this line, and then y varies between 0 to 1, correct? So this is one of the domains or one of the situations which Fubini theorem allows us to handle, isn't it? So we can easily compute. All you need to do is compute partial derivatives, set their squares, put them in this formula, and compute it. Okay, so you are going to get this double integral. Okay, so you have to verify each and every step that partial derivatives exist, they are continuous. Okay, and the domain is such that you can compute the double integral over it. Okay, so now when I do this, I can, this is the Fubini theorem. At this step, at this step we have used the Fubini theorem, because this is the definition of surface area, and this area is this by Fubini's theorem. Now you see, this is a constant function with respect to y, so you can integrate, and then when you put y equal to x, you are going to get this, and 0 is just going to be 0. And now you see, this is an integral of just one variable. Okay, so you have to know how to compute this. Okay, I did not do the computation because this is you should do it, and one way to just take make a change of variable. Okay, so in the case of single integrals, the method of substitution or method of change of variable and so on. Okay, so you do that, but what I'm saying is you have to be careful that the domain is such that you have to verify that domain is such that you can make use of that Fubini's theorem. Okay, so do this. I give you one more example over here. Find the area of the part of the paraboloid. Okay, now these are the surfaces which we had drawn in the beginning. Now in the cross sections are again the parabolas, correct? Z and X, you see this is parabola, and Z and Y is also a parabola. So these are this is a parabola, and then this is also a parabola. So this is what and this is under the plane Z equal to 9. So that is why this 9. So you cut it from the above in the the positive direction of Z by this plane Z equal to 9. So only this much of the surface you are interested in, and you want to find the surface area of this. So all this thing, correct? All this thing you want to find the area of this. Okay, so here the domain is not given explicitly, but once you draw this and you see that this is cut by Z equal to 9 plane, so if you look at the projection of this, you are going to get a disk, correct? The boundary is going to be basically this, and then all the interior point will be the will be the projection of this part. Okay, so the domain is not given, but you can find it out by taking the projection onto the xy plane, and we get the problem of then computing the surface area, which will translate to computing a double integral over this domain, correct? So I have written it over here. So by the formula of the surface area, if I am interested in to compute the surface area of this particular surface, I am supposed to compute this double integral. Okay, but there is a small problem here because the domain is a disk now. Okay, it's neither a rectangle and nor it's bounded by two curves, correct? So there is a small bit of problem over here, but the disk is such a nice thing, we should be able to compute double integral over this. Okay, so we are going to resolve this problem slowly. Okay, so as I said, there is a small issue over here, that the domain is neither a rectangle or nor it's of the type which Fubini's theorem tells us to how to handle. Okay, so this is the Fubini's theorem which we stated. Okay, so we need some idea to make sense of this double integral. So what we are going to do is we will transform this D, okay, into a simpler domain which Fubini's theorem allows to handle. Okay, so this is going to involve the idea of change of variables. Okay, so this disk we will try to transform, but these things, that we can use the polar coordinates, isn't it? And then we can transform this integral. But how does one transform the integral? Because domain, that I can express it in terms of r and theta, but with this transformation, how is this integral going to transform? Okay, so we are going to have a discussion, or we are going to develop the idea of change of variable for double integrals, and the same situations will be there in the case of triple integrals also. Okay, so we are going to have those discussions, and we will do it in the next lecture, that how to transform a given integral over a domain which we are not able to compute just by using the Fubini's theorem. But if we make a suitable change of variable, then the domain transforms into a known type which can be handled using Fubini's theorem. Okay, so this is the question, or this is the idea which we are going to discuss in the next lecture. As I said here, we have not discussed an example of triple integral in the form of Fubini theorem which we just discussed in the beginning. So let me just give you one example. In fact, I am just going to recall example from previous lecture. So you remember we had this question that find the volume of the tetrahedron. Okay, and to do this we had used the idea of double integral. Okay, because what we did, we looked at this surface, so this surface, and then the domain was okay, this one over here in the xy plane. So we computed the double integral of this surface over this domain, and that gave us the volume which we wanted. Okay, but here we can also use the triple integral. Okay, I'll tell you how. So already you have the domain in the xy plane, and you see the limits for z variables. So z is from z equal to 0, which is the xy plane, to this surface which is given by this. So if I bring in one more integral, that is going to give me a triple integral. So the integral in xy, an integral in z, and you see this is precisely the situation which Fubini's theorem allows for triple integrals, that z is varying between two surfaces. Here the surfaces are planes. Okay, they can be complicated surfaces also. So once we realize this, then the limits for x and y we already have from our previous lecture, and the limits for z are going to be this, and there is no function here to integrate, so that's the constant function 1. So the volume can be also written as a triple integral. Okay, so dv without any function over here. Okay, and just set the limits, and this is just a simple integral you can compute. Okay, so you will see that the answer is also going to be the same. It has to, correct? So these are the ideas which you have to decide. See, once you know too many things, so sometimes you have to use the formula or the situation which gives you the answer easily. Okay, so that will also happen, that one question may be solved using two different ideas. Okay, so you have to take the decision on the spot that which one is better. Okay, so I'll stop here, and the next lecture we start talking about the idea of change of variables. All right.